So in the last lecture, we have discussed single phase half wave controlled uncontrolled rectifier, and that was our diode. Now we will be changing it to some other loads. Like here, we will be changing it to inductive load. Let's start our. It is also a single phase half wave rectifier. Single phase half wave rectifier. Half wave rectifier. But the load uncontrolled rectifier. Uncontrolled, but the load is L load. Okay, so if you draw the circuit, so this is my circuit and this is my L. Okay, so what happens, the this is my Vs, so it is nothing but Vm sine omega t. Vs is equal to Vm sine omega t. We have to take out the voltage across this V naught, and we have to take out the voltage across this, that is VD. So I am already specifying VD as this side positive and this side negative, and I have to take out the current I naught. So actually I have in the last lecture we have discussed about the loads, okay, voltage stiff load and current stiff load. So I have placed this as a current stiff load because the nature of the current will be changing. So if you remember in the when we have discussed the R load, there we have found out about your voltage. But because voltage and current have the same waveform as it was voltage is stiff load. But here voltage and current will have different shape. Therefore, we will be concentrating on your inductor, current of that inductor. Okay. So what happens that there will be a two cycle operation will be there. So this is my, let us draw first. Actually the issue is with the drawing only. So this is my sinusoidal waveform and this is my Vs. Okay, this is my V naught, this is I naught, and this is VD. So VD, voltage across diode. So this is my omega t. This axis is always omega t. Just remember that this axis always remains omega t for every cycle. This so actually you are drawing a waveform in terms of in a function of I of omega t. So what happens when your SCR is on during the positive half cycle? Your potential this is positive and this is negative. So during the positive half cycle your diode will be forward bias because of the because forward bias, and it will be off. So you can what happens is that the circuit will be like this, right? Short circuit. And as the diode is your ideal diode, there will be no voltage drop or any resistance connected conduction loss. I have already explained. So using the KVL equation, if you write down, if you apply the KVL equation, what you will write? You can write Vs Vm sine omega t is equal to V naught. So V naught is L d I of omega t upon dt. Okay, I of omega t upon dt, because I is will be your function of omega t. That's why I have written I of omega t, and Vm will be your voltage across your sinusoidal. So if you are now going to find out the I of omega t, that will be equal to Vm sine omega t dt, and L will be divided here. So integration of this term. So it is d omega t, right? So you can write it like this. So integrate these things, you will get this. So if you integrate I of omega t, so you will be getting integration. So you are actually integrating in terms of dt. Okay, so this omega will come down. So you will write like this: Vm upon omega L, and sine omega t integration will be minus cos omega t, and there will be one some constant term k. Okay, so this is the equation which you are going to get of your waveform. Now let us discuss what are the initial conditions and what is the, like, suppose during I we can say that when omega t equal to 0, I of 0 will be 0. Let us assume this is your initial condition. So if you put the value here, I of 0 0, then 0 is equal to Vm by omega L, Vm by omega L cos 0 is 1, so that will be minus 1, right? Plus k. So k's value, if you find out, it will be k is equal to Vm by omega L, and k is equal to Vm by omega L from here. And if you put the value here, Vm by omega L, k is equal to Vm by omega L by initial condition. Okay, so what about the equation? I of omega t will be Vm by omega L, take it common, 1 minus cos omega t. So this is one of the important equation. If you draw the waveform, what will happen? Suppose this is the pi by 2 axis, right? And this is my 3 pi by 2 axis. Now I'm going to draw I of omega t. This is nothing but I naught of omega t, right? This is the output current, or you can say that the source current is also equal to your output current. Now at this point, this is my 0 point, put the value 0 here, cos 0 1, 1 minus 1 will be 0. So overall your point will be 0, right? Next, this is my pi by 2 axis, pi by 2. So pi by 2, cos pi by 2 will be, put the value cos pi by 2. So you have to put value 0, pi by 2. Okay, and sorry, uh, pi by 2, and then 2 pi and 2 pi. You will get the waveform from here. So if you put 0 here, so 1 minus 1 will be 0, pi by 2 will be 0, so your value will be Vm by omega L. So this value is Vm by omega L. Vm by omega L. Okay, at pi by 2. Next is your, you put the value pi. This is my pi cycle. Put it here. Cos pi is minus pi. So you will get 2 Vm by omega L. Just put the value, check it around. You will get these values. You don't have to do much. So it will be 2 Vm by omega L at pi by 2. So your, what happens, your waveform, if you draw the waveform, you will get this type of curve. So if you draw the waveform, join these points. Okay.